Up to this point, we have solved linear equations and quadratic equations. Now let's look at some other kinds of equations, and it'll turn out that we can use some of the techniques that we used in solving quadratics on the equations that we see here. Here we have a third degree equation, and we can actually factor to solve it. We're looking for a common factor here. It turns out to be 5x. We pull 5x out of this term and we're left with 4x squared. We pull 5x out of this term and we're left with minus 25. And we look to see if we can factor further. Oh yes, this is the difference of squares. So we factored that difference of squares into the sum of terms times the difference of the same two terms. So it turns out to be 2x plus 5 times 2x minus 5. Now we ask ourselves, what value of x will cause each factor to become 0? Now I know that we actually have two factors here, but I'm treating it as though it were one. It's one common factor that we had here. What value of x causes this factor to be 0? It's easy to identify. It's 0. So when x is 0, this factor becomes 0, and therefore the entire equation becomes 0, or the entire expression on this side becomes 0, and therefore we have a true statement and therefore a solution. The value of x that will cause this factor to be 0 and this factor to be 0 is not just self-evident. So it might be that we would do this to find the value of x that causes 2x plus 5 to be 0. We say, I'd like to know what value of x will cause 2x plus 5 to be equal to 0, and then just solve this little linear equation, subtracting 5 on both sides and then dividing by 2. We find x to be negative 5 over 2. In a similar way here, we would set this equal to 0 to find x to be 5 over 2. All right, so our three solutions to the equation. Here we have an equation involving 4 terms, and again we want to use the method of factoring. And remember, when we're faced with 4 terms to factor, we use the method of grouping. Now grouping these two together, let's say I'm looking for a common factor. Oh, it looks like x squared. So I snag x squared out of those two terms and I'm left with x plus 2. In these two terms, I see that 3 is a common factor, so I pull 3 out of those two, and I'm left with x plus 2. And then I look at the two terms remaining, and these two terms have a common factor of x plus 2. So we pull x plus 2 out of those two terms, and we're left with, let's see, out of this term, we're left with x squared. Out of this term, we're left with 3. Now, we look to see if we can factor further. This is not the difference of squares. It's unfactorable. So we want to identify solutions, and we're looking for the value of x that will cause each factor to be 0. I'd like to know the value of x that causes this factor to be 0. Oh, it's pretty evident that that would be negative 2. So x equals negative 2 is one solution. The other solution is found by setting this factor equal to 0 and solving. Now I see that we can use the extracting square roots idea, because we have a single variable quantity squared here and a real number involved in our equation. So I can set x squared equal to negative 3. X then is plus or minus the square root of negative 3. So x is plus or minus the square root of 3i. So now I have two imaginary solutions and one real number solution. Now I want to point out a situation that often gives trouble in this environment, where we have a string of factors. It's often thought that when you take out a common factor, that x equals 0 will always end up being one of the solutions in our string of solutions. And that's just not the case. Look at these two factored forms. They look an awful lot alike. And the only difference is that x appears up here and x doesn't appear down here. If we're identifying solutions up here, we would say that x equals 0 is a solution, x equals negative 3, and x equals 3. Those are our three solutions, just by asking ourselves what value of x causes each factor to be 0. But when you ask the same question down here, you know that x equals negative 3 and x equals 3 will be solutions. But x equals 0 is not a solution here. Even though you had a common factor of 5, there's no value of x that will cause this factor to become 0, you see. And therefore, x equals 0 is not a solution. It's a very commonly made error here, and I want to make sure that you don't make that mistake. All right, consider this next problem. This one involves three terms, and when you have a polynomial of higher degree and only three terms involved, just use your general method of factoring. We know that when factoring trinomials, we're kind of anticipating that it's going to factor into a binomial times a binomial. And so we just go with that idea. What times what is x to the fourth? Well, probably x squared times x squared to give x to the fourth. Now look at the sign pattern. We have a plus sign here, so the signs are the same. This sign is negative, so it's minus minus. Factors of 2 are just 2 times 1. Let's verify the middle term. Minus 2x squared minus 1x squared would be minus 3x squared. So this is a correct factored form. Now we would try to factor further. Well, we can factor here because it's a difference of squares. So we'll bring down x squared minus 2 and factor this into x plus 1 times x minus 1. Well, it's easy to identify the solutions involved in those factors, but what about here? Well, to identify the solutions involved here, we would set x squared minus 2 equal to 0 and solve. Adding 2 on both sides, x squared is 2. And by the square root property, or by extracting square roots, x is plus or minus the square root of 2. All right, 2 irrational solutions. The other solutions are x equals negative 1 and x equals 1. So our 4 solutions to the equation. There is another way to deal with this kind of problem. This is an equation that is quadratic in form. Quadratic in form. I'm not going to go through the whole thing here, but it is a technique that applies in other situations and is necessary in other situations. Here it's not necessary because we ended up factoring in quite successfully. But I just want to show this to you. If we're recognizing that this x to the fourth can be written as x squared squared, and this can be written as 3 times x squared to the 1 power, and then this is just plus 2. That here's the quadratic form. Now the quadratic form is where we have a variable quantity squared in the first term, and that same variable quantity to the first degree in the second term. And we have that here. Here's the variable quantity squared here to the first degree here. Now, it doesn't make any difference what that variable quantity looks like. It happens to be x squared itself here. So we could actually cause a substitution to take place and say, okay, let's let a letter like, let's say u, stand for x squared. And now you see we can rewrite this in terms of u and solve it for u. You see, we can say that u squared minus 3u plus 2 equals 0. And now factor this into, well, let's see, how does it factor? It factors into u minus 2 times u minus 1. And here then u would be 2 and u would be 1. But are these the solutions that we want to the original equation? No, because the original equation involves x, and this involves u. So we'd like to know the value of x, not u. So here's what we do. We back substitute. We let u be x squared, and let's let x squared take the place of u. So this u is x squared equals 2, and x squared equals 1. And now we would, by extracting square roots, x is plus or minus the square root of 1, which is plus or minus 1, which we found earlier. And here, x is plus or minus the square root of 2. So we get the same result by performing a little substitution. It was probably easier, I think, though, to go through the factored form that we went through before than it is this substitution method, but this substitution method will come up again. When radicals appear in equations, the general concept for solution is to isolate the radical term, the term involving the radical, and maybe the radical itself, and then undo the radical by performing an inverse operation. Here, for example, is an equation involving this radical. I want to isolate this radical on one side, and I can do that by adding 5 on both sides. So I'll get the square root of 3x plus 4 equals 5. Now, to undo the radical, to undo square rooting, you see, we can perform an inverse operation, squaring. So on this side of the equation, I'm going to square to undo the radical But if I square on the left, I need to square on the right to maintain the balance in the equation. Squaring the square root, we get the radicand. And on the right, 25. Subtracting 4 on both sides, it's easy to see that we get 21 on the right. Dividing by 3, we find x to be 7. Okay, now, in performing this squaring operation on both sides, sometimes extraneous roots are created. We create roots that we really don't want. They're really not solutions to the equation. So for that reason, it's pretty important to check the solutions. Let's check to see if x is a solution here. 3 times 7, 21. 21 plus 4, 25. The square root of 25 is 5 for this term. 5 minus 5 would be 0. 0 equals 0 is true, and so this is indeed a valid solution. Let me show you another way to work this problem, another just general concept here, because it's going to come up a little bit later. There is another way to write the square root of 3x plus 4, and that is by using a fractional exponent. Let's say that I use, bear with me here a second, let's say that I do this. I take this radicand, contain it in a parenthesis, and write this to the 1/2 power. Now I can think about the problem a little bit differently. I can think about the problem as one where, gee, I want to take this side of the equation and raise it to an exponent that will undo the 1/2. In other words, I can raise it to a power that is the reciprocal of this. The reciprocal of 1/2 is 2. So I'm going to square just as I did before, and we end up with the same result, but it's the idea that 1/2 times 2 is 1, so we get the 3x plus 4 equals 25 as we would expect. But it's an interesting technique to take a reciprocal power here as our tactic for removing that radical. In this one we have a radical involved, and there are several other terms. To isolate the radical now, I can put the radical term on either side of the equation. I've elected here to put the radical term on the right by subtracting 9, the square root of x, on both sides. In doing that, I bring down 2x minus 5, and then minus 9 root x appears on the right. Now my prescription is I could further isolate the square root of x. That is, I could divide throughout by -9. It would create fractions over here. Either a single fraction, 2x minus 5 over -9, or two separate fractions involving -9 in the denominator. Now if I do that, though, I can anticipate some rather difficult algebra facing me, because I'm going to have to square on both sides to clear the radical. So what I might elect to do is just leave the problem as it is and just think of it like this. I'm just going to take this side and square it, and this side and square it. Because right now, it's not too tough to square this binomial. Well, let's see what I get. I'm going to square this to get 4x squared. Double this product is minus 20x. And then square the minus 5 to get 25. That's not too tough. And on the right, when I square the -9, I get 81. Squaring the square root of x gives x. So not too tough. All right, now let's move the 81x to the left side. Subtract 81x on both sides and collect, and we get this. Now this is where I want to pick up the problem. Up to this point, it meets all of the requirements for our concept of solution. Isolate the term involving the radical and then square on both sides. Okay, next we want to factor. And it's an interesting factorization that occurs here because the middle term has a coefficient that's incredibly large. Now that leads to a creative factorization. You see, that it might be thought that once we start the factoring process, we would use 2x times 2x to give 4x squared. And then 25 logically would begin with 5 times 5. But the middle term is so really big that we have to kind of make those splits unusually, well, we need to make the splits in an unusual way. 4x squared becomes 4x times x. And then for 25, we're going to make 25 times 1 instead of 5 times 5. Now we know that this product along with this product will give the middle term. And I'm going to subdivide or split the factors of 25 as 1 times 25 so that 25 can be multiplied times 4. 25 times 4, you see, is 100. All right, now I failed to look at the signs. I should have looked at the signs a little bit earlier, but the last sign is positive, so these two signs are the same. Middle term is negative, so it's minus minus. Now let's verify the middle term. We have 4x times 25, or excuse me, 4x times negative 25 is negative 100, and then x times negative 1 is negative x. So negative 100x minus 1x minus 101x. All right, so the correct factored form. Now we'd like to identify the values of x that will cause each factor to become 0. Let's see, I can't see through this very easily, so I'll say what value of x will cause 4x minus 1 to be equal to 0. Add 1 on both sides, I get 4x equals 1. Divide on both sides by 4, I find x to be 1/4. Then for this one, it's pretty evident that x needs to be 25. Now once again, it's kind of important to check. We would find out in checking that this is a valid solution and this one is not. So x equals 1/4 is the only real number solution here. In this next problem, notice that a radical is implied with a fractional exponent. And in this circumstance, in isolating the term involving the radical, we're just isolating this x plus 3 to the 4/3 power. Now, remember from before, and I'm adding 16 on both sides to get 16 on the right here. Now remember from before that this fractional exponent means we have a cube root involved here and we have a power of 4 involved here. So we're taking this binomial and both raising to the 4th power and cube rooting. All right, that's the idea. Now, to undo this, we can use the technique we talked about a little earlier. That is, we can take this side and raise it to an exponent that will undo this. And that just means raise it to the reciprocal exponent. The reciprocal of 4/3 is 3/4. So raise this to the 3/4 and we're out of trouble. But if we raise this side to the 3/4, we have to raise this other side to the 3/4. So we're doing this. All right, now this is relatively trivial. When we multiply those exponents, we get 1. So this side is x plus 3. On the right, though, we have the 4th root of 16 cubed. Now, it's probably better, more prudent if we can do so, to take the 4th root first and then do the cubing. You see, we're going to look at it like this. 4th root of 16 is 2. 2 cubed is 8. So x plus 3 equals 8, and then we subtract 3 on both sides to find x to be 5. Now, it's important again to check that solution. Let's see, we have x plus 5, x is 5, so 5 plus 3 is 8. We have the 4/3 power. Now, the cube root of 8 is 2. Aha, 2 to the 4th power is 16. 16 minus 16 is 0. 0 equals 0. Truth, this is a valid solution. Here's a problem containing two radicals. Now, when two radicals occur in an equation, you put them on separate sides of the equation and perform the squaring operation. And you're hoping that the equation involves nothing but those two radicals. You want one single radical over here and one over there. Well, we don't have that here. We have a situation where we have a couple of radicals, but we also have another number, another term involved. So we still separate radicals on one side and the other, and then we're going to go through the squaring process to try to clear the radicals as much as possible. All right, I have elected to subtract this term on both sides to separate the radicals. Now what I'm doing is this. I'm taking this side and squaring, and this side and squaring. When I square here, I get x minus 20. When I square the binomial, let's see, the fast way is first term squared plus 2 times this term times that term. You see, 2 times the product of those two terms. And then the last term is the last term squared. So I'm indicating that here. Now I recommend if you go through this process that you write this step, that you don't try to evaluate as you go along. Certainly not in something as complicated as this. 10 squared is 100. 2 times 10, 20. So we have negative 20 root x. And here we have plus x. Now we see that we still have an equation involving a radical. So we have to go through that idea, that concept again. That is, we need to isolate the term involving the radical and square on both sides. So we have to go through it again. Let's kick these two terms to the other side by subtracting 100 and subtracting x on both sides. We get this. Then the x's go out. Minus 20 with minus 100 is minus 120. And now I can clearly isolate root x if I divide on both sides by negative 20 at this point. On the left I get 6, on the right the square root of x. Squaring on both sides I find x to be 36. Now it might be pretty important that we check this. After all, we squared twice, so chances are we could have created an extraneous solution. Let's go through and check. If x is 36, the square root of 36 is 6. All right, 6. 36 minus 20 is 16. Square root of 16 is 4. 6 plus 4, 10. 10 equals 10. Yes, this is a valid solution. The concept when fractions are involved in equations is to identify a common denominator and multiply through by the common denominator to clear the fractions. Now that's true whether the fractions are algebraic fractions involving variables or whether they're just common ordinary arithmetic fractions. Now here the common denominator involves every different factor that we see. So the common denominator involves 3 and x plus 2. So we would want to write the common denominator times each term. So it would be 3 times x plus 2, which is the common denominator, times this term. And then the 3 times x plus 2 times this term. And then the common denominator times 0 is going to be trivial on the right, so I'll just put 0 over here. I do want you to notice that I put the factors involved in the common denominator right in between the minus sign and this fraction. I just popped them in there. I just injected them into this term, and that's perfectly all right. All right, let's see. We can see our cancellations here. The 3's go out, and we have x plus 2 times x plus 1. We want to go ahead and multiply those out. We get x squared. Let's see, the middle term is 2x plus x, that's 3x. And then 2 times 1, 2. And then here, the x plus 2's go out, so we have negative 3 times x plus 1. Well, that's negative 3x minus 3, all equal to 0. I'm seeing this as a quadratic equation, so let's solve it using one of our methods. We'd like to factor probably. Gee, I need to collect some like terms here first. We have x squared, 3x minus 3x. Oh, they go out. We have 2 minus 3, that's negative 1. Oh, good. I have no first degree terms, so I can use the method of extracting square roots. I add 1 on both sides to find x squared to be 1. X then is plus or minus the square root of 1, or plus or minus 1. So x is plus or minus 1. Now, it is important, again, to go back and check to make sure that these are valid solutions. And once we perform that check, we find out that these are both valid solutions. When equations involve absolute value, the first order of business is to put the absolute value business on one side of the equation and everything else on the other side. This equation is already in that form. So we have the absolute value of some expression. It's a very simple one in this case. And then all the other stuff in the equation is on the other side. Now once you've accomplished that form, just understand the meaning of absolute value. Absolute value is distance from 0 along the number line, but what we might want to do is just ask ourselves, what value would make this true? That is, what value of this expression would make this statement true? Well, we know that the absolute value of either 5 or negative 5 would be equal to 5. So x is either 5 or x is negative 5 to make this true. And we can follow that same kind of logic pattern even when the item within absolute value symbols is an expression like this. We can say, gee, what number would go here to make this true? Well, either this number is 5 or negative 5. So we can then split this into two cases. And one case is that either that expression is 5 or that expression is negative 5, and then solve the two equations. Here we're adding 2 on both sides, so we find x to be 7, And here, adding 2 on both sides, we find x to be negative 3. Let's verify these solutions. If x is 7, we have 7 minus 2, that's 5. The absolute value of 5 is 5, so a true statement. If x is negative 3, we have negative 3 minus 2, that's negative 5. The absolute value of negative 5 is also 5. A true statement. These are solutions. Even when the equations get complicated like this, we can follow the same tactic. That is, we can think to ourselves, to make this true, that the number in here either is the same as that number or the number in here is the opposite of that number. So we split into our two cases then like this. We say either it's the case that x squared plus 6x is equal to 3x plus 18, or x squared plus 6x is the negative of 3x plus 18. And now solve the two equations. Back over here, we recognize a quadratic equation, so we kick all the terms to one side and factor. I've got x squared over here. I'm going to subtract 3x on both sides. When I subtract 3x over here, I'll get 3x. And when I subtract 18 on both sides, I get minus 18 on the left. Now factoring, x times x for x squared. The last sign is negative, so we have the plus minus combination. And factors of 18, whose difference is 3, would be the 6-3 combination. So 6 goes here, 3 goes here. Values of x that cause each factor to become 0 are negative 6 and 3. For this other one, it's the same idea. We have a quadratic equation, so we want to simplify a little bit and then throw all the terms to one side. The simplification is over here where we're dropping the parenthesis. We have negative understood 1 times each of these. We get minus 3x minus 18. Now let's see, I'm adding 3x on both sides, so when I add 3x over here, I get 9x, and I'm adding 18 on both sides, giving me plus 18 on the left. And once again, factoring, let's see, all signs are plus, so we have the plus-plus combination. Factors of 18, again, the 6-3 combination is what works here. Values of x that cause each factor to become 0. X is negative 6, x is negative 3. Notice the solutions. Negative 3, negative 6, 3, and negative 6. Negative 6 is appearing twice as a solution, so there are only 3 distinct solutions, negative 6, 3, and negative 3. It would be worthwhile to go back and check these as solutions, but they do turn out to be valid. Here's a problem that leads to a rather unusual equation. Now, we've been looking at some different kinds of equations here in this segment. And I want to just show this problem because a rather interesting equation emerges from it. It says a deposit of $2,500 in a mutual fund reaches a balance of $3,052.49 after 5 years. What interest rate on a certificate of deposit compounded monthly would yield an equivalent return? There is an equation that concerns itself with an amount of money in an account given a certain initial investment over a certain period of time at a certain interest rate. And that's the formula that we use to solve this problem. That formula looks like this, and this is really what I want to show you for this problem. It's A equals P. Now, A is the amount in the account after a certain period of time. P, the principal, the amount of money initially invested. R is the rate of interest, and it's an annual rate of interest. N is the number of compoundings per year, and N appears again here, and T is the number of years. Now, in our problem, we're talking about finding an interest rate associated with a growth of some investment from an initial principal of $2,500 to an amount of $3,052.49. Now notice the fraction here, R the interest rate we're looking for, N the number of compoundings. Well, we were talking about monthly compounding, so that would mean 12 compoundings per year. And now the NT is 12 times 5, and that, of course, will be 60. Now I want to show you a manipulation here with the equation so that we can use our calculator to calculate this rate of interest. And it's a manipulation that essentially puts all of the well, we're solving for r, and we're putting all of the other elements on the other side of the equation, but it's not necessarily the case that we have to perform calculations as we go. For example, from this step, if I want to begin the process of isolating r, I would divide on both sides by 2,500. Now when I divide over here by 2,500, I get this fraction. When I divide over here by 2,500, this disappears, so I simply have this. Now, to continue the isolation process, I see that a variable expression is raised to the 60th power, and I want to somehow undo that. Well, I'm going to use the technique that we talked about before, where we take this and we just raise this to an exponent, which is the reciprocal of that one. You see, we're raising power to power. And in doing so, if we multiply reciprocals, they'll take one another out and we get 1. So I really want to just raise this to the 1/60th. And this is equivalent to taking the 60th root, you see, of that side of the equation. Well, if I do it over there, I need to do it over here. So I have this side also to the 1/60th. All right, that's the idea. In the next step, I have this, and then 60 times 1 over 60 is simply 1, so I have 1 plus r over 12. Now subtracting 1 on both sides, I would get this. And now I want to clear the 12, so I multiply by 12 on both sides. Now once I do, the 12 will go out on the right, and I'll be left with r. And then 12 is multiplied times all of this business. So I have 12 times all of this. Now, once we jump into the calculator, we want to start from the inside of the parenthesis, from the innermost symbol of inclusion. You want to perform this calculation first, and then press the exponent button and open a parenthesis and enter 1 divided by 60 and close parenthesis. And at that point you can press enter, you see, and calculate this if you want to, and then take that amount, subtract 1, and then take that amount and multiply times 12. Now once done, we find that the calculation is right at 0.04, which is 4%. So our certificate of deposit would need to be earning an annual interest rate of 4% compounded monthly.